this lecture, we will learn about the linear approximations and the differentials. The approximation of a function y equals f of x at a point a f a is given by this formula. L of x, L for linear approximation of the function x is f at a plus f prime a times x minus a. So this is the linear approximation, or you can also think that this is the tangent line approximation of the function f of x at x equal to a. You can also write this as f of x itself, but with approximation symbol. So the first example, find the linear approximation of the function square root 1 minus x at a equal to 0, and use this to find the square root of these two decimal values. So let's do this. You want to first read carefully at what point are you finding the linear approximation at a equal to 0. So do write a equal to 0. And then you write f of x equals the function given square root 1 minus x. Evaluate this at 0. So this is square root 1 minus 0. Simplify, you get 1. Now you want to write f of x square root 1 minus x, but this time you want to derive the function. So let's derive this. You can also write this as 1 minus x to the 1/2. When you write in the exponent form, the square root terms, it's easy to derive. So do the power rule of differentiation. It's 1/2, 1 minus x, half minus 1 is negative half. But understand that this is also the chain rule, so differentiate this again, dot negative 1. So this dot is from the chain rule. You're differentiating 1 minus x again, and you get this. So let's rewrite this as negative 1 divided by 2, and the square root term can be written in the denominator, the negative exponent, as 1 minus x. Now let's evaluate this at 0. F prime 0 will be negative 1 over 2 times square root 1 minus 0. So this is negative 1/2. Now we are all set to calculate the linear approximation, which is L of x is given by the formula f at a plus f prime a times x minus a. So let's write L of x. A is 0 for the problem, so let me plug in, write f0, f prime 0 times x minus 0. X minus 0 is same as x. Now we did calculate f0 here. f0 was 1, so let me plug in, and f prime 0 let me plug in as negative 1/2 times x. So you can rewrite this expression as 1 minus x over 2. So the linear approximation of the given function square root 1 minus x is given by 1 minus x over 2. Now let's try to calculate the square root of decimal values using this linear approximation formula. So square root 1 minus x is the given function, and the corresponding linear approximation of this given function square root 1 minus x is 1 minus x over 2. This is what we found just now. So now let me choose some x value, say x equal to 0.1. The idea behind choosing 0.1 is when you plug in 1 minus x, 1 minus 0.1 will give you 0.9. So let me plug in 1 minus 0.1. On the right hand side, I have 1 minus 0.1 divided by 2. The left hand side I can simplify, write it as 0.9. Right hand side simplify 0.95. So the square root of 0.9 is 0.95. Similarly, you want to choose one more value of x, which leads us to the square root of 0.99 value. So this time we choose x equal to 0.01. Plug in 1 minus 0.01. So this is 1 minus 0.01 divided by 2. Simplify the left hand side, it's 0.99. Simplify the right hand side, it's 995. So the linear approximation of the function square root 1 minus x is 1 minus x over 2, and we also were able to find the square root 0.9 and square root 0.99 value by assuming a suitable x value and plugging in back to the linear approximation formula, which is 1 minus x over 2 for this particular problem. Now I think I have one more example. Use a linear approximation to estimate the value of 8.06 to the 2/3. So let's start with f of x equal x2 to the 2/3. And this time we're going to write a equal to 8 for the problem. So let me calculate f at a. Sometimes the a value is given, like the previous example, a was 0. Sometimes it's not given. When it's not given, you're good to assume the a value, but it should be a nice neat value with which you can evaluate the function without using a calculator. So I don't choose a decimal value here, but at least the nearest nice neat whole number to 8.06 will be 8. So let's calculate f of 8, 8 to the 2/3. So this can be written as, after simplifying, you're good to write this as 2 to the 3 and then 2/3. 8 is 2 to the 3. Now the exponents can be multiplied. So when you simplify this, you're good to multiply them. And the 3 cancels when you multiply. So all you have is 2 square, which means it's 4. Now let's do the derivative f prime x. So it's 2/3 x to the 2/3 minus 1, the power rule. I'm going to derive this function. So I have 2/3 x to the negative 1/3. Then I have this derivative f prime x, which is 2 divided by 3 times x to the 1/3. Now let me calculate this functional value at 8, the derivative value at 8. So it's 2 divided by 3, 8 to the 1/3. 8 to the 1/3, 8 can be written as 2 to the 3 and then 1/3. So when you multiply the exponents, 3 and 1/3 get cancelled. So all you get is just 2. So you have 2 divided by 3 times 2, which is 1/3. Now that we have the functional value at 8 and the derivative value at 8, we are all set to plug in to the linear approximation formula. So let's plug in. L of x equals fa plus f prime a times x minus a. So L of x equals f at 8 plus f prime 8 times x minus 8. So all we are doing here is we are plugging in a equal to 8. So f8 was simplified to be 4. So let me use that here. Plus the f prime value here we did calculate, it's 1/3 times x minus 8. So let me rewrite this as 4 plus 1/3 x. I'm multiplying this 1/3 to both the terms, negative 8 over 3. Simplifying again, I get x over 3 positive 4 over 3. I'm simplifying the fraction 4 and negative 8 over 3. Now that we have a nice neat approximation of the given function was assumed to be x to the 2/3. Again, the reason is you have 8.06 to the 2/3. So the 8.06 is rewritten as a variable x, and then the 2/3 remain the same. So the linear approximation of the function x to the 2/3 was this. Now we are good to plug in the x value. So let's write, take x value to be 8.06. When you plug this back here, the expression becomes 8.06 to the 2/3. The right hand side becomes 8.06 divided by 3 plus 4 over 3. This can be simplified and you get 4.02. So the linear approximation of 8.06 2/3 is 4.02. So we were able to calculate the approximation without using a calculator, but using a linear approximation formula. Next is the definition. If y equal to f of x is a function where this function f is differentiable, then the differential ERENTIAL differential dy is then defined in the terms of dx by the equation. So given an expression y equal to f of x, say you're doing a differential of dy, y variable, you get dy, and then you're differentiating the function f, you get f prime. When you get f prime, it's a function of x, so you also add a differential dx. So in the next example, so differential means it's a small increment. So let's use the concept of differential in the next example. So the function f of x is x plus 1 divided by x minus 1. Now let me derive this f prime. It's a quotient function, so I use the quotient rule. So square the denominator, always start with the denominator, derive the numerator, it's 1, negative, write the numerator, and then derive the denominator, again it's 1. So multiply this negative to both the terms here, simplify. You have x minus 1 negative x negative 1 divided by the square term in the denominator. So you're good to cancel these x and negative x, and all you have is negative 2 divided by the square in the denominator. So now write the formula for the differential. Differential of the function y is dy equal to the derivative f prime times the small increment dx. So dy in the problem remains the same dy, but we did find f prime to be negative 2 divided by x minus 1 the square times dx. So the differential of the given function is this. In the next example, you are given a graph and suppose that the only information we know about the function is the functional value at 1 is negative 6 and the graph of its derivative is shown below. So the function graph, when you read this, the y-axis is not the usual y, but it's the f prime. And the x-axis is x. So this is the derivative graph given. So this is the derivative of the function f given. Given this, you are asked to use a linear approximation to estimate the value of f of 0.95 and f of 1.05. Had we been given the function f of x, then we could have used the linear approximation formula like our example 1 and we would have done that. But without the function being given, you are given its derivative graph, not even the function graph, but just one functional value. You are asked to calculate the value of the function at different points, 0.95 and 1.05. So let's do this. I want you to read the derivative graph carefully. Again, we all understand the y-axis is not the usual y, but if you read any value, it's the f prime value. And this particular graph is your f prime function, and x-axis is x-axis itself. Exactly at 1 on the x-axis, I want you to read the y value, which means the f prime value, which is 2. So I want you to write that f of 1 is negative 6, it's given for us, and f of f prime 1 from the graph is 2. As soon as you read f of 1 is 6, you are able to make out that this is your f of a, which means your a is 1. And also list what are the things you want to find in the problem. You want to find the functional value at 0.95 and the functional value at 1.05. Having been listed like what you want to find, now you're good to write the linear approximation formula. L of x equals fa plus f prime a times x minus a. This is the formula we learned in this section. We also know that a is 1, so let's plug in. Let's write f1 plus f prime 1 times x minus 1. F at 1 value is given and we already listed here on the top. So let me write it as negative 6. F prime 1 was readable from the graph. and we did make out that that value is 2, so let's plug in, and then we have x minus 1. Now we are good to multiply this 2 for both the terms. So we have negative 6 plus 2 times x is 2x, and then 2 times negative 1 is negative 2. Simplify this a little bit, you get 2x negative 8. Now all we have is the linear approximation of the given function is 2x minus 8. You're asked to calculate the functional value at 0.95. So you're good to plug in 0.95 here. So you have 2 times 0.95, negative 8. Simplify, it is negative 6.1. Similarly, you're asked functional value at 1.05. So plug in 2 times 1.05 negative 8. Simplify, all you have is negative 5.9. So without knowing the exact function, which can be an algebraic or any trig function, say the function f of x can be a negative x square or e to the x plus 1 or x square plus 5x, something like this. This in particular is not given here in this problem. The function was not defined, but you are able to calculate the functional value at some particular value, say 0.95, 1.05, by using the linear approximation. So we'll end this section 3.9 as well as the chapter 3 here.